are going to be discussing the assembly and sampling process for the HRPP, or High Resolution Passive Profiler, for PFAS analysis in groundwater. So these are solid stainless steel samplers. They were made with the ability to be coupled together using these adapters with the threads on either side. Each is about 4 feet long, and we have successfully coupled 5 samplers together for a deep groundwater analysis in the field. We also have pointed adapters to put on the bottommost sampler in order to make the process of driving these samplers into the ground easier. They are typically deployed with a DPT rig, direct push tooling, or we've also used a vibrocore on a boat to deploy these into the sediment below a pond. So the sampler itself is made of solid stainless steel. They're about 4 feet long, as I mentioned before, and we have 3 different types of cells on each of these samplers. So we have equilibrium cells. This particular sampler, there are 3 sections of equilibrium cells. Some samplers have more or less sets of equilibrium cells in order to kind of capture what data you want to get out of that particular depth of your deployment. So if you're more interested in velocity, we do have versions of samplers that have more velocity cells, or if you're not very interested in velocity, we do have samplers that only have equilibrium cells so that you're able to get the highest resolution data that you are able to. So starting at the top, our equilibrium cells here. This particular sampler has 3 sets of 5. There are paired depth cells that each contain about 10 milliliters of pore water once equilibrated. So maximum resolution is about 2 inches. If you need more volume for your sample analysis, you could also couple multiple depth pairs together in order to achieve the volume that you need. On either side of these, we have velocity cells. They come in sets of 4 for the modeling of groundwater velocity based on the equilibrium of our bromide tracer solution through these cells, which each have a different specific surface area when combined with the cover plate, which I'll talk about in just a moment. That allows us to take the mass transfer of our bromide through the membrane and model it to predict the pore water velocity outside of these cells. We also have here a through hole for bioset beads that goes all the way through to the back of the sampler here. If we were to use bioset beads for these projects, we don't currently use them for PFAS analysis, but that is possible to do in the future if we are looking for microbial data or CSIA. This through hole here allows us to store the bioset beads, and they will come into contact with the pore water on both sides through a membrane mesh that prevents them from escaping. For the velocity cells here, there are 2 cover plates. First is the lower cover plate. If you can see here, we have multiple different sizes of openings that align with the multiple depths of these cells, which gives the cells their specific surface area and allows us to model the velocity. All of the components used for the assembly are stainless steel. So our cover plates are stainless steel, as well as our screws. This is to make sure that nothing is rusting as it's sitting in the pore water as it equilibrates. Once these are deployed, it will take about 3 to 4 weeks to come to a full equilibrium that we can then measure the extent of using the bromide tracer solution that we assemble the samplers in. And I'll discuss a little bit about each of the membranes for these samplers because they do differ for PFAS analysis. Starting with our equilibrium cells, we have, as I said before, a set of 5, and there are 2 more on either side here. We have the stainless steel cover plate, which has been machined to sit flush with the top of the sampler for an easy deployment. The assembly order for these cells is to first put down a cut Viton gasket. This gasket will go around the openings of equilibrium cells and help to seal the cover plate down once we assemble it. Next, we have a stainless steel membrane. This is a 0.2 micron pore size, and we found that using this stainless steel membrane as opposed to previously used nylon membranes prevents more absorption of PFAS to the surface of this. We want to make sure that we're not having too much absorption to the surface, because that will hinder the equilibrium process and possibly take longer than expected to equilibrate with the pore water. Then after that goes on, since this is a rather robust membrane, we don't have a protective layer, we just have the cover plate, and this will be held down by stainless steel screws. Moving to the velocity cells, we have a lower cover plate and an upper cover plate. So the lower one will go inside the lower indent here. First, we have another Viton gasket. Each of these has a different opening width. It'll be easier to see with the cover plates. So when you're assembling these, you want to make sure that you're lining up the screw holes and that you're also lining up the opening areas correctly to the volume cells, or else we won't be able to properly model the velocity of the groundwater. So typically you have your smallest opening on your deepest cell, or the cell with the most volume, and your shallowest cell will have the largest opening. Again, the cover plate looks just like that Viton cutout. There are two smaller openings and bigger openings. We want to align those bigger openings with the smaller volume cells. Now, once that is assembled, this plate will get screwed down just to make sure that it stays put while we add on the top. Next, we have another Viton gasket here. This one has cutouts for those velocity holes and also for the bioset beads if you are choosing to use those in your deployment. That goes on top of the inner membrane, or the inner cover plate. And on top of that, we put our nylon membrane. This, plus the other two layers that will go on, were used in the optimization of our velocity model, so we must keep the amount of layers and the thickness that we use the same in order to correctly model. So our first layer is that membrane. Next, we have a fine mesh. This is a nylon mesh also. This is another protective layer for that nylon membrane to help prevent puncturing. And lastly, we have a coarse stainless steel with the screw holes cut out, and this is just another protective layer for that nylon membrane because it is a little bit easier to rip, and we want to make sure that when we're deploying the samplers and pushing them into the ground and pulling them out, that there aren't rocks or other objects that are going to push through these and puncture them, because that will invalidate the data we're trying to collect. So, coarse stainless steel mesh at the top. And lastly, we have the top cover plate. Again, the opening for the bioset beads and our velocity cells here. We need to make sure that they're lined up properly. And those are all of the cell types on this particular sampler for PFAS analysis. And our fine nylon mesh, it's about 10 microns. Our nylon membrane filters are 0.45 microns. Moving on to the assembly of the HRPP, we have here a setup with a trough with our sampler submerged in a bromide tracer solution. This is typically 100 to 200 milligrams per liter in distilled water. However, depending on where you are deploying the HRIP, you will need to adjust that concentration. You want to make sure it's 50 to 100 times greater than the concentration in the surrounding groundwater so that a good equilibrium can be established. So we have the sampler fully submerged in the solution. This trough here is pre-cleaned before we get to the field with water and methanol as well to make sure there's no residual PFAS. And now that we have our sampler submerged, we're going to begin by taking a clean syringe. We're going to draw up some of that bromide tracer water, and we're going to inject this into all of the screw holes. Make sure all of the extra material that may have found its way in there. Make sure there are no air bubbles, because again, those air bubbles will hinder the interactions between our membrane and the surrounding water and affect the equilibrium time. So once you have gone in and cleaned out those screw holes, you'll want to do the same with the cells. Just kind of run the syringe around the outside, make sure any air bubbles that are sticking to the sides are removed, and this will be the same for the velocity cells. So we have the two small screw holes in the bottom plate, our upper plate, and I can already see in here, since submerging the sampler, we have some air bubbles that have stuck to the inside of these cells. So I want to go ahead and dislodge those, make sure that there's nothing sticking. And once I'm confident that there's no air left in the cells here, we can begin our assembly. I'll start with the equilibrium cells. As we mentioned before, there are 3 layers to our equilibrium cells. Our first one is the Viton gasket. We're gonna put that in the water. Again, make sure any of those air bubbles that might stick to the sides are removed, and align that gasket with our equilibrium cells here. Next is our stainless steel mesh. This is our membrane. It has been pre-cut so that our screw holes are outside. Here, we don't have to worry about punching those in the field. It allows us to be a bit more precise. And once we are confident that that is fully submerged and there's no air bubbles, we're going to go ahead and take our cover plate, submerge that, and align that on our sampler cells. Now that everything has been submerged, there's no air bubbles to be seen. This can be tacked down with some screws. These are also stainless steel, as I mentioned before, and we typically assemble using a drill. However, once you assemble these and tighten them up, the Viton tends to relax a little bit, so we go in and tighten them again a little bit later, a couple minutes after assembly, to make sure we have a good tight seal. And I'll mention as I assemble here, before we go to the field, we will take all of these samplers and test the screw holes, test the fit of everything to make sure that when we get into the field, there will hopefully be no surprises. And for the sake of time, I'm just going to put a handful of screws in. There are 12 screws on these particular equilibrium plates, and after we have finished assembling the entire sampler, we will go back and hand tighten these with another screwdriver just to make sure that if that Viton gasket relaxed a little bit, that we're still getting a good seal between the equilibrium plate and our sampler. So that way, the only interaction of our pore water and our water inside our cells is through our membrane, and we're able to know the mass transfer coefficient of what's going through there, and that will help with our sample analysis later. Moving over to the velocity cells, these have two plates, as I had mentioned before. We're going to start off with our first gasket, the Viton gasket. We have our screw holes pre-drilled, and we have our two larger size holes and two smaller size holes. These are going to line up with our different cells here, the different volumes for our modeling of the groundwater velocity. So I want our larger size hole to be on the most shallow velocity cell and the smallest hole over the largest volume velocity cell. Make sure that those screw holes are lined up and there's no air bubbles. We'll then add that small velocity cover plate. Again, making sure those screw holes are aligned and that the openings are in the correct order. We'll then go ahead and connect this plate down. Just to make sure we get a really good seal for our velocity modeling. And then after that, we have our membranes to assemble. So the first membrane that goes on is going to be the gasket, actually. This gasket is going to cover up that first initial velocity plate. Gonna make sure again that there's no air bubbles, that our holes are lined up properly. And on top of that goes our nylon membrane. So again, making sure there's no air bubbles and everything is wetted down. That is going to lay on top of these cells like so. You'll notice there are no screw holes pre-cut into this or on this nylon membrane. We will be making our own holes after these are assembled to make sure that we're covering as much surface area as we can here. So now I have that protective fine nylon mesh. I'm going to add on the coarse stainless steel here. And once those are all together and aligned, last up is the cover plate. And again, on the top of this cover plate, you can see our smaller surface area openings are over what was the larger velocity volume cells, and the larger openings are over those smaller volume velocity cells. Now we kind of want to situate that plate so that it's in its little indent and sitting flush with the top of the sampler. And now that we have all of that here, we're going to take just a little awl. It doesn't need to be super sharp, but sharp enough that you could easily poke a hole through that thin nylon membrane. And what we're gonna do is we're gonna hold our cover plate down, keep those membrane layers in place, and just use this tool to poke a hole right where there's our openings in the cover plate for our screws. While we're holding it down, that membrane does not move, and we're ensuring that we get a good seal between that cover plate and the membrane and gasket. So now we have holes in each of these, and we could go ahead and put our screws in for this plate as well. And again, for the sake of demonstration purposes, I'm only going to put a few of the screws in. And that is how you assemble the layers of the velocity cells. This will be repeated on the other velocity cells here and our equilibrium cells on either side as well. Now that we have this sampler fully assembled and theoretically we have all of our cover plates on, we're gonna go back with our screwdriver and just do one more hand tightening. And before we go ahead and deploy these, we need to make sure that we know the concentration of the bromide tracer water that we assembled them in. So we'll take several samples of this bromide water through the day. This will also serve as a blank to ensure that there are no PFAS that found their way into our bromide tracer water. And as long as we know the time-zero concentration of this bromide solution, we are able to calculate our velocity after we retrieve these from the field and look at the concentration of bromide that remains in these velocity cells. Overall, these samplers take probably about 20 minutes each to fully assemble. They could be stored in the bromide water, as I said before, until they are deployed, just so there is no evaporation of that tracer water from the cells. And this is ready to be deployed. Now let's talk about sampling the HRPP. So when this is retrieved, it's typically not going to be this clean, but when you pull it out of the ground, you're going to have some soils and sediments on here, probably caked onto your equilibrium cells. That's okay, leave it on there until you are about to sample. So what we're going to do is, in order to make sure we're getting the fullest amount out of each of these cells, we're gonna raise one side of the sampler up just slightly. You could use a syringe, you could use a screwdriver, whatever you happen to have on hand, just to get a little bit of a slant so that all of our sample is going to pull more towards one corner of these equilibrium cells and we're able to extract as much as possible. Next, we'll take some clean Kim wipes and remove any sediment gently. If you happen to have some sediment kind of caked on there, we will be using syringe needles here, and the caps of these actually fit very well on the outsides here. So if you need to get into the corners, because you want to make sure that you're not going to sample the sediment, we want only what is inside of our equilibrium cells and not any of the water that is on the outside. With that in mind, the first thing we're going to do is take a clean needle. This is going to break the vacuum on each of these cells. So we're going to put it at the uppermost point and push it in just enough to relieve that vacuum from the inside of the cell. Then we're going to take a clean syringe for each set of cells. One thing we want to double check is when we're preparing this syringe, you do want to pull back the plunger just slightly when we are sampling so that when we're drawing the sample up, it doesn't have a lot of contact with this rubber septa, just to prevent any possible absorption of the PFAS onto that material. So next, we're going to take the syringe with the stopper pulled out slightly, and we're going to put it down at this lowest elevation corner of the equilibrium cell, right to the bottom. And we're going to slowly draw up that sample water from inside the cell. These each contain about 10 milliliters. Because we pull the stopper up slightly, that might mean we have to go in twice to pull out the full volume. We store our samples in typically these 15 milliliter polypropylene containers. Pull the syringe out and transfer your sample. Because I don't feel like I got quite all of the sample out, I'm going to go back into that first puncture hole and pull up until I don't have any more sample being removed. So this is slightly over 10 milliliters of one equilibrium cell at that specific depth. This will be repeated for all of these cells using a fresh syringe and a new sample container each time. If you need to combine samples, you can do that in the field or later on. But for each time you are piercing one of these, you need to make sure that you have this vacuum seal broken, or there's a possibility that when you draw your sample up, there will be water pulled through that membrane and added to the pore water that was equilibrated through the membrane before. And we want to make sure that we're only sampling what has come to equilibrium through that membrane over the deployment time. The same goes for the velocity cells. These are just slightly different in that we have more layers to poke through, but we follow the same procedure. So again, you're going to take a clean needle, you're going to poke it in one side so that you have room to sample on the other. Now we'll take a clean needle. Each of these will be sampled by a clean needle because they will have different concentrations of bromide left in the equilibrium cells, and we want to ensure that we're not cross-contaminating them so we get the most accurate results from our velocity modeling. We're going to take the clean syringe again. We're going to put it into the lower side where our tilt is, so we're able to get as much of that sample water out as possible. Now these have smaller volumes than the equilibrium cells. So pulling all of our water out of this cell, we have about 2.5 milliliters of sample. That is one sample. Each of these velocity cells here, each of these 4 will have their own sample to be analyzed separately for the modeling purposes. After all of your cells have been fully sampled, you can go ahead and remove your screws, disassemble the HRPPs, and give them a good rinse on site to make sure you're not bringing those contaminated sediments home. But you want to make sure that you are sampling them when they are fully intact without any of the cover plates or anything removed, to ensure that we're only sampling the pore water that is equilibrated through that membrane.